So in the last video, we saw that what the problem is, the problem statement, and we set down the goal mathematically. Now in this video, what we're gonna see is that how we can solve that particular goal methodologically. All right. So let's recall what your W was. So remember that our weight was defined as the time that A waits for B, right? So you can say that that many of you would have been able to recognize that we'll have to define W using case analysis. And in fact, that's the case. So when A arrives before B, so that's how we note this down, that A arrives before B is by saying that A curly arrow B. All right, so in that case, the weight is TB minus T, which is the time at which B arrives minus the time at which A arrives. And in other situations, it would be 0 because A arrives after B, so it does not have to wait for any time at all. All right. Now, and what is that we want to calculate? So again, mathematically, what we want to calculate is this distribution function of the random variable W, all right, for any given value sigma. Okay, but we know that what this sigma will range from. The sigma is going to be ranging from 0 till E minus S, right? Because the least A can wait for B is 0. That is, it does not wait for at all because either it arrives at the same time as B or after B. Or in the maximum it can wait for is E minus S, because in that situation, A arrives at start time while B arrives at the end time. All right. So, and remember that in the last video, we also saw that, for the case when sigma is 0, then it's a very peculiar case because unlike typical continuous random variables, we observe that the probability at one particular event is 0. But this random variable is kind of peculiar in the sense that for just one case when W sigma is 0, when the weight is 0, the probability there is not 0. Okay. Which is kind of peculiar, and that's why we are not currently dealing with that particular situation. But for any other value of sigma, so that is to say that for any non-zero sigma, what we are interested in is to find out a distribution function. All right, which means that from the mathematical definition of W, the only situation that we have to see is the first case, which is to say that when A arrives before B. All right, and in that particular case, we know that W is nothing but TB minus TA. All right. So therefore, so this is something that we had left with, is that how we can express the distribution function in terms of the probability. So here we are going to simplify our probability, or what we're gonna, our aim over here is to find out what this probability could be. All right, so the probability that W lies between sigma and sigma plus D sigma is given as the probability that TB minus TA lies in this range. And this follows from what we just discussed, that for non-zero value of W or for non-zero value of sigma, the weight is nothing but defined as TB minus T. So it's just simple mathematical substitution. This can also be written as the fact that we want to calculate the probability of TB belonging in the range TA plus sigma and TA plus sigma plus D sigma. Okay, so that's just like rearrangement of TA from left to the right of the set inside. Now note that TA is a random continuous variable, and therefore we can calculate this probability using the marginalization trick. Now you might be aware of the marginalization trick from your undergrad lectures on probability and stats. And now what this trick is, I'm gonna write this down, okay, in a second. But this is a very common trick and can be used, in many general problems. All right. So what trick is that? Remember, our goal over here is to find out this probability, and the problem is that we cannot simply evaluate this probability using the fact that TB is uniformly distributed. All right, so one may say that, well, if TB is uniformly distributed, the probability that we are trying to find out is nothing but T sigma divided by E minus S. Okay, and this is for those of you who know that this just directly follows from the fact that TB is uniformly distributed. But remember that this is, now it may look as if and it may actually give you the right answer, But the point is that this is not methodologically correct. And the reason is that, TA is also a random variable, right? So note that in the probability that we are set to find out, TA is also a random variable. All right. So your answer, I mean, not your answer, but your solution did not account for the fact that TA is a random variable. So we also need to take care of that. All right. And that's why, why we are doing this marginalization trick and etc. Okay. But we'll soon see that we can actually take care of this TA very easily, and that's exactly because of the marginalization trick. Okay, so here's that trick in front of you. So the probability that TB lies between TA plus sigma and TA plus sigma plus D sigma can be given as this. All right, so observe that in the first step what I did was I introduced another variable. I mean, this random variable TA is already there, but I introduced this explicitly in the probability term via a comma sign, right? And if you note, then this comma sign is used to indicate joint probability. All right, so here I'm evaluating the joint probability between your original event and this new event, that TA is alpha. All right, and those of you remember, the reason we do this is so that we can then marginalize out the other variable that we just introduced. Okay, and this is the marginalization trick that I was talking about. So I introduced TA in this joint probability, and because I did that, I will have to marginalize out this variable, and that's why there is the summation sign over alpha. All right, and this is a marginalization trick, to say it again. Now, in the second step that I did was I converted this joint probability into the product of conditional probability and a prior probability. All right, and as it's written in the blue ink, that is nothing but just a simple application of the Bayes formula. All right, so yes, okay, so that's what it is. And in the next step, it turns out that it's a zero. All right. Now you may wonder that why is that the case? What's the source here about it? So note that I had emphasized earlier that TA is a continuous random variable and has as it has been for a in several occasions throughout this video and the last video as well, that it's really important for you to understand the difference between continuous and discrete, right? So essentially, because it's continuous, the probability that TA is going to be one specific value alpha is a zero, and that means that if you're summing over finite or infinite values, it does not matter, the sum is always going to be zero, because you are summing exactly zero quantity. Okay, whether you sum finite times or infinite times. So even if alpha is infinite, there are like infinite space over which you're summing over. That does not matter because you're summing exactly zero. And it exactly is. Okay, so probability that TA is going to be alpha is uh, exactly zero. Okay, if whether or not you believe it. Okay. So what's the wrong? Okay, so what is it that we are doing wrong? Right, so what we are doing wrong is that instead of integrating, we did the summation. Well, I should not say that that we should do integration over summation. Okay, because integration is nothing but summation. What we need to understand is that because TA is continuous, so we cannot use this formula. Instead, we have to use the formula corresponding for the continuous random variable case, and that involves that what we are summing over is the product of conditional and the prior probability. But the prior probability, instead of saying that the random variable is some specific value alpha, we say that that random variable lies in certain range. Okay, and again, this is because that we are dealing with the continuous random variable. So everything is the same except for the fact that a very tiny difference, that the event on which you're, for example, conditioning upon, or the event on which you're multiplying the prior probability of, that changes to the event which says that the random variable lies in a certain range. Okay, and that range is like for example, in this particular case, it's going to be alpha and alpha plus d alpha. All right, so that's the only change that we do, and we know that the summation still carries over. The only difference is that because again there is like d alpha involved, and there is like summation, we know that from calculus this is nothing but integration. All right, so coming back, so the probability that we set out to solve was the probability that TB lies between TA plus sigma and TA plus sigma plus D sigma, which is again, we want to again use the marginalization trick that marginalization trick will give us summation over some joint probability, and that joint probability can be written as conditional times prior. So the conditional thing is mostly the same, except for now, what you want to condition upon, as I just said earlier, is the event that says that TA lies in a range that is alpha and alpha plus D alpha. All right. So this is the only change that we have to do. So TA lies in the range alpha plus D alpha. And again, what we multiply with is the probability that TA lies in alpha and alpha plus D alpha. But we know, right, from again, a lot of times, you might have seen this earlier, that probability is actually nothing but the density function of TA times D alpha. All right. So the prior probability has just been substituted with this product. Okay, that's it. And then we also know that in the limit D alpha tends to 0, this summation is going to be nothing but the integration. So that's why there's an integration that you can see from S to E. Okay. Now let's simplify this further. All right. So note that we say, so here we can actually simplify this conditional probability. All right. So in the last step, we conditioned the probability that TB belongs in a range. We condition it on the event that TA lies in a range, that is alpha and alpha plus D alpha. So intuitively, and also this is the case that what you can do is that you can substitute in the value of TA. All right. And so this is what you'll get, that the earlier conditional probability that you set out to calculate is actually nothing but the probability that TB lies in the range alpha plus sigma and alpha plus sigma plus D sigma plus T alpha. All right. And all I did was to substitute in the values of TA, right? Because what you want to calculate is conditioned upon that event, right? So it's basically saying that we assume that TA lies in this range, and that means that if we assume TA lies in that range, so all that we have to do is substitute in the values. Okay, so this is like kind of an obvious mathematical logic, but if not, it may help you to go back and know more about implications in mathematical logic, right? But yes, okay, this is like simple how you do how do you solve or use implications in mathematical logic. All right, now so let's see how we can simplify this further. Okay, so and voila. Okay, so now it turns out that we can actually get a closed expression from this step onwards. So note that indeed we can. Why? Because the probability that TB lies in this range can now be easily evaluated via integration, right? Okay, so we integrate the probability density function of TB from the range alpha plus sigma and to alpha plus sigma plus D alpha plus D sigma, then this will actually give you the probability that you're looking for. And then, so this is what I did in the inner bracket, and then I multiplied it with, and the rest of the thing is the same. And on, just simple arithmetic, what you get finally is the thing that you can see. And then on further solving it, the outer integration, you get D sigma divided by E minus S, right? Remember, I also substituted the density function of TA with 1 upon E minus S, right? Because remember, TA is also uniformly distributed between S and E, right? The another thing that I want to point out is that the integration that you can see on the second last step is kind of weird, because we see D alpha square, right? So here I'm just using a hack to say that D alpha square is nothing but 0, because D alpha is tending to 0. All right. So that's the only hack that I'm using, and yeah, okay. From that, it now just follows, what's on your screen, that this final integration is nothing but D sigma divided by E minus S, and that means that your W, the density function of your W is nothing but 1 upon E minus S, right? Because remember that we are just applying the earlier formula that your W, your density function for W can be written as, the probability that you calculated for W lying between sigma and sigma plus D sigma divided by D sigma, and take the limit that D sigma tends to 0. Okay, so fortunately your D sigma is just 0 over here. Sorry, your D sigma is like appearing very wonderfully. So if you divide it by D sigma, you can just cancel that term, and when you do the limit evaluation, that will just turn out to be 1 upon E minus, right? So this is your density function. Okay, now let's so let's see if our answer that we have found out is correct or not. Okay, Let's see. So what's one way that, we can verify if our solution is correct? So remember that, this is one of the laws of probability, that on your entire sample space, your density function should integrate to 1. All right. So let's see. Okay. So we know that, the probability that W lying between 0 and E minus S should be 1, because that's the least and the maximum it can go. All right. And we know that this is actually nothing but probability that W is 0 plus the probability that W lies between 0 and E minus X, excluding 0. Right? And remember, the reason we are doing this is because, here the W is kind of a peculiar random variable that, it has a non-zero probability mass over W equal to 0. Right? So that's why we are doing this. Right? Now let's see how we can further calculate this mathematically. So your LHS can be written as half plus this particular limit. Half follows from what we had discussed in the last lecture, that y probability that W is going to be 0 should be half. The other thing is also kind of obvious, although it looks peculiar, because I've introduced a variable I've introduced a variable delta, and I've also put a limit. And the reason is obvious, because remember that the probability that we want to calculate is for W to lie between 0 and E minus S, but excluding 0. So the way you can exclude 0 is by using the fact that we are taking this limit. Okay. So you can always, pause here and check that indeed this is like one of the correct ways to do it. Okay. So yes. Okay. So let's further simplify this. So you can substitute in the value of the density function for W that we found earlier, which is 1 upon E minus S, and do this integration. So the integration that you'll get is, and upon application of the limit, is nothing but E minus S minus delta divided by E minus S. And then when you apply the limit of delta tending to 0, then you'll get 1, right? So this LHS actually evaluates to 3 by 2, because half plus 1. And unfortunately, this is not 1. So the solution that we obtained is wrong. Okay, unfortunately. So that's quite surprising, because all that we did was quite methodologically. So what's the mistake that we did? So what I would like you to do is maybe see what's wrong in this video, and in the next video, I will upload the or I'll explain the correct solution, or the errors that we did in this method. Okay. Thank you, and best of luck.